yesterday, and we'll be discussing some important concepts as well. Yeah, give me a second. I'm just opening a document. Guys, just wait for 1 more minute. We will start the session exactly at 6:25 p.m. Just give me a sec. Just give me a minute. Yeah, I'm sharing my screen. Yeah, I hope you are able to see my screen, right? And able to hear me, right?
Yes, sir.
Yeah. So in the yesterday session, I'll just revise in just 1 or 2 minutes what we discussed in the yesterday session. So in the yesterday session, we discussed about operational amplifiers, what is an op amp, and its different kinds of properties, its operation, and we derived the mathematical expressions for the output voltage, how the output voltage varies based on, we discussed different conditions, right? And we focused on inversion and summing, and then difference. I think for differentiation and integration we haven't yet explored it. We are just done with uh, summation, and let me check in the PDF. Yeah, we have discussed about all these mathematical expressions, right? Derivation and everything, how these expressions have been the final expressions have been derived. So yeah, initially we started the session by discussing about virtual ground. So we discussed the concept of virtual ground, and then we discussed about the feedback, positive and the negative feedback. Uh, so when the negative terminal, we also discussed that in op-amp there are two terminals. One is inverting terminal and non-inverting terminal. Why they are called as inverting and non-inverting terminals, right? And we discussed about the concept of virtual ground, where the voltage at the specific node Vx is equal to 0. And then we discussed the positive and the negative feedback, and then we derived the expression for the summing, how an op-amp can be used as an for some summation. Okay, all these things we discussed, and we obtained the expression by applying the uh, you know I1 plus I2 plus I3 is equal to IF. So from that we derived the final expression V out is equal to minus RF into sigma I is equal to 1 to n V of I Vi by Ri. Okay, and then we have discussed a few conditions like what happens if R1 is equal to R2 is equal to R3 is equal to R. So then V out is equal to minus RF by R into V1 plus V2 plus V3. If RF is also equal to R, then V out is equal to minus of V1 plus V2 plus V3. Then we, this kind of amplifier, we call it as the inverting sum amplifier. And then we have discussed about other conditions like RF is not is equal to R1 is not is equal to R2 is not equal to R3. So all are different. Okay, again the same expression, just I told you, right? Yeah, the same expression but another form of representation. V out is equal to minus of A times of V1 plus B times of V2 plus C times of V3, where A is equal to RF by R1, B is equal to RF by R2, C is equal to RF by R3, where these A, B, C are scaling factors, okay, for voltages V1, V2, V3 respectively. So this kind of mechanism we call it as a scaling mechanism, scaling function. Okay, and then RF by R, if it is equal to 1, then it is considered as an inverting sum amplifier. But if in case RF by R, if you take it as 1 by n, where n can take any value, for example here we have taken RF by R is equal to 1 by 3, where n is equal to 3, then V out becomes minus of V1 plus V3 by 3. So this is the averaging operator, because average means sum of observations by number of observations. So if you want an op-amp to perform the averaging operation, so what are the conditions that we need to follow? The first thing is like R1 is equal to R2 is equal to R3 is equal to R, and RF by R, if you take it as 1 by n, where if you take the n value as 3, or else in other words R must be equal to 3 times of RF, where RF is the feedback resistance. Okay, so in this particular condition, in this scenario, the output voltage become equal to the average of the input voltages, but here it is inversion is taking place. Okay, so we discussed the scaling, summation and averaging operations, and we also discussed how to convert a negative voltage into a positive voltage with the help of inversion. Okay, where here we are using two operational amplifiers. The first op-amp is responsible for the summation, and in other words, to be more precise, inverted sum. Okay, and the second op-amp is responsible for the inversion. So it will be converting the negative value into the positive value. Finally, from the output of the second op-amp, you will receive the positive value. Okay, the voltage which is exactly equal to the sum of the input voltages. Okay, so this is the thing we discussed yesterday. Now we need to discuss about in case of non-inverting amplifier. We discussed the inverting amplifier yesterday. Today we need to discuss about non-inverting amplifier. Up to here everything is clear, right? Till inverted amplifier. Yeah. So today we need to discuss about non-inverting amplifier. So in case of non-inverted amplifier, so actually here what we need to do is like, so first we need to take, see, in case of non-inverted, what's the difference between the inverted amplifier? If you just observe the circuit diagram, the schematics, so what's the difference that you can observe between the inverted and non-inverted amplifier? Here I am having the non-inverted amplifier, okay, where the input signals voltages are applied to the inverting terminal of the op-amp. But in case of non-inverting amplifier, the input signals are applied to the non-inverting terminal, which is represented denoted with the positive sign. Okay, for this another terminal we are applying the input voltages. So apart from this, here you can find one resistor, right, which is labeled as RA. Okay, here you can find one resistor which is connected to the negative terminal. Okay, which is the inverting terminal. But here in this case, if you just look into this particular scenario, so no resistor is placed for the non-inverted terminal. If we are operating it in the inversion, if you are trying to build something like inverted summation amplifier or else inverted averaging amplifier, so whatever it could be. But in the case of inversion condition, inverted op amp, we are not connecting any kind of resistor to the non-inverting terminal. But here we are connecting it to the non-inverting terminal. We are, directly we are not connecting it to the ground. So in between that we are having a resistor. Okay. So actually the thing is, there is one concept called compensation resistor. So I just don't know how many of you know about it. So any idea about compensation resistor? Compensation resistor. Any idea? Sri Krishna, do you have any idea about compensation resistor? Okay. So actually we discussed about pull up and pull down resistors, right? Pull up and pull downs. And we discussed about current limiting resistor, maybe in the ECED course. So similarly, there is also one kind of, see, it's actually a terminology, just a naming convention. There is something called compensation resistor. See, actually in the actual schematic, we have not connected any kind of resistor to the this particular amplifier, right, for the positive one, non-inverting terminal. If we are supplying the input voltages to the inverting terminal, we have not connected any kind of resistor to the non-inverting terminal. But practically, if you just observe some schematics which are found in the online, here also you will find one additional resistor. Okay, for this non-inverting terminal also you will find one additional resistor, which is actually called as compensation resistor. If you are operating this particular op-amp operational amplifier in the inverting, if it is acting as an inverting amplifier, if you found any kind of resistor to the non-inverting terminal, that specific resistor is called as the compensation resistor. So why we use a compensation resistor? So we already discussed in the yesterday's session, there is something called offset. Okay, in op-amps there is something called offset. So this offset is completely a random quantity, okay, which varies from one op-amp to another op-amp. And again, this offset is further classified into two different categories. One is positive offset and another one is negative offset, isn't it? So offset is arised because of the imperfection in the fabrication. So due to some limitations and imperfections in the fabrication, less accuracy, low precision. So due to fabrication issues, these offsets arise. Okay. So these offsets are classified into two different categories, positive offset and negative offset. So to prevent this offset, an additional resistor is placed, which is actually called as the compensation resistor. Okay, if somewhere else you came across additional resistor placed with along with the, placed in the path of non-inverting terminal, despite you are operating this op-amp in the as an inverting amplifier, then just don't confuse that additional resistor which is placed is part of some correcting the offset. Okay, it is part of correcting the offset to reduce the effect of offset. To be more precise, to reduce the effect of offset, an additional resistor is used which is referred as a compensation resistor. I hope it is clear right now. Is it clear, Sri Krishna? Yeah. See, coming back to non-inverting amplifier, by default itself, it becomes a standard practice to use resistor over here. Okay, in the case of a non-inverting amplifier. In case of inverting amplifier, sometimes you may find an additional compensation resistor. Sometimes you may not find. Okay, so actually these op-amps are classified into three different categories. Okay, actually these op-amps are classified into three different categories. The first category, which we call it as the general purpose op-amps. Okay, general purpose op-amps. And the second one is high precision op-amp. And the third one is, the first one is general purpose and the second one is high precision and the third one is fast acting op-amps. Okay, so in terms of response, in terms of how quickly an op-amp responds for the given input, already we discussed one important parameter yesterday. I hope you remember that, right? I'll show you that slide very quickly. So actually these concepts are very very important because op-amps plays an important role. Okay, so actually there are so many books on IC, integrated circuits, and design related books, and there are so many books available even from Cambridge University and different things. So in every book, you if you take it as a reference, everywhere you will find that for op-amps highest priority has been given. Yeah, I think this is the parameter we discussed yesterday. Slew rate. So slew rate is one important parameter of an op-amp which indicates that how fast an op-amp is responding uh, to the given input. Okay, yesterday we discussed the theoretical part related to the slew rate, but we haven't gone through the graphical analysis. So what kind of input you are giving and what kind of output you are getting. So that analysis we haven't done, the graphical analysis. We will do that graphical analysis today. So apart from this, actually these op-amps are classified into three different categories. The first one is general purpose op-amps, and the second one is high precision op-amp, and the third one is fast acting op-amps. Okay, all these three op-amps, different categories of op-amps, will have different slew rates. Okay, even within the same category of op-amp also, again different op-amps are there. Different op-amp manufactured by different company will have different slew rate. Okay, and also one more thing. So usually op-amps are constructed using, during the manufacture, these op-amps are constructed using uh, transistors, right? We already discussed yesterday. In olden days, op-amps are made with the help of vacuum tubes. Three vacuum tubes used, right? Out of them, two are one category and another one is one category. So we discussed about it. Two are for differential input, and another test tube is for output stage. So two test tubes are for differential input stage and one test tube is for the output stage. So in generally speaking, usually in the present day op-amps, around 20 transistors are used. So out of these 20, so many of the resistors are NPN, sorry, 20 transistors are used. So among these 20, so mostly they are NPN transistors. So very few PNP transistors are used. Especially at the, in the schematic, maybe something like related to the current mirroring. At those kind of aspects, these PNP transistors are used. So NPN are fast acting. Okay, so NPN transistors respond very quickly. So that's why many NPN transistors are used. So actually not only with the transistor, but with the help of a bipolar junction transistor, and with the help of BJTs, MOSFETs, JFETs. So using them also op-amps can be constructed. Okay, so op-amps are not only made with a transistor or BJTs, bipolar junction transistor, they are also constructed with the help of MOSFETs or JFETs. Okay, field effective transistors, right? MOSFET and JFET, junction field effective transistor. Yeah. So shall we go to the next part, everyone? Everyone, shall we move to the next part? Yes, Prakash, I think you are having some question, right? Prakash Sharma, you have any questions?
सर आपने ये एनपीएन और पीएनपी ट्रांजिस्टर बताया, इनका यूज क्या है कीकैड में?
You can use op-amps in KiCAD also.
हाँ.
There would be a separate library called P. Already we discussed one session on Spice library, right? I hope you remember that, or else you can go to the recording. So in that Spice library, P Spice, to be more specific, there is one P Spice library. So under that library, there would be op-amp, okay, LM741. So you can use that operational amplifier. These op-amps are widely used in making of PCBs. Okay, like having some specific role. Let's say you want to produce some triangular wave. Okay, you want to produce, see, actually till now you might have worked on making cloning some kind of sensor, or else some board, microcontroller board. Let's say you might have cloned an Arduino Uno, or else you might have
Yes.
cloned something like Arduino Nano. So this is one aspect of PCB designing. Okay, and another aspect is to make some kind of a PCB which is having some specific role. Let's say you want to generate some kind of signal, triangular wave, you want to produce some triangular wave. okay, or else you want to produce some square wave. So you can use op amp to produce a triangular wave also. Okay, so op amps play an important role. They can perform all kind of mathematical operations. It can perform differentiation, it can perform integration, it can do addition, subtraction, multiplication, division. So it can do all kind of mathematical operations. So that's why it's very essential to understand.
Okay, sir.
Yeah, because see, actually, as per the course, I need to directly go with the circuit diagram. I need to place an op amp and I need to do some connection and I need to produce some graph and I need to show you the output. Okay, so but rather I'm explaining you how these expressions, how an op amp can be operated for different purposes. How can we perform addition and subtraction, differentiation, integration, how we can do all these things. So the mathematical analysis and the circuit diagram, because if I don't explain this theory behind the op amp, you may not be able to know what is a compensation resistor, what is a feedback resistor, how to provide an input to an op amp, and what is the concept of virtual ground, and all this stuff you may miss. So that's why I'm explaining these concepts. Yeah, so we will go without any delay. Already it's been so late, we will directly jump into the further concepts. So today we will discuss about, instead of the another amplifier, now we will discuss about how an op amp can be used as an integrator. Okay, in case of if you are using op amp as for normal basic operation, fundamental operations like addition, subtraction, so for that you can use linear elements like resistor. But in case of using op amp as an integrator, you need to take help of reactive elements like capacitor and the inductor. See, I'll show you the circuit diagram. So this particular circuit diagram that I'm showing you right now, so this can perform integration. Okay, isn't it amazing? Just a simple circuit diagram. We are using an operational amplifier. Apart from an op amp, we are using some one capacitor and one resistor. Okay, just a capacitor, a resistor, and an op amp. That's it. You can do integration. If you provide an input sinusoidal voltage, it can do the integration. So, for example, I will ask one question. So if you have given something like, for example, you have given a sinusoidal wave, okay, to the V in, okay, at the input terminal, you have given a sinusoidal wave. So what would be the output of, what would be the output if you check the output with the help of oscilloscope by placing the probe at V out, and if you check the output graph in oscilloscope, so initially you have provided a sinusoidal wave. What would be the output wave? Anyone?
Negative cos.
Negative?
Cos.
Yeah, perfect. Because for sine wave, it is expected that if you do integration, what is the integration of sin x?
Negative cos.
Negative cos. But we are doing this with the help of inverting terminal. Again, minus of minus, it will become what?
Positive cos.
Cos a positive cos. It's not negative because already integration of sin x itself is a minus cos x. But we are doing this integration with the help of inverting terminal, not the non-inverting terminal. So that's why minus of minus cos x, it will become cos x. So you will get a cos x, cosine wave. Okay, positive cosine wave. No phase shift. Okay, no 180 degrees turn. Directly you will get a cos wave. Okay, as the output. So now we need to analyze mathematically how this particular circuit can really make an integration. So we will prove it with the help of the mathematical analysis. So the first point here is like, in order to do the mathematical calculation, see, we are providing an input wave V in. It could be any kind of wave, not only a sinusoidal wave. You can give a square wave, you can give triangular wave, whatever the wave it could be. For example, for simplicity, let's assume it's a sinusoidal wave. Okay, or else you can take any wave. Okay, no issue. So we are providing some input. Okay, input current, which is denoted with I in. I in refers to the input current, and here there is one resistor. Okay, and from here it is currently in negative feedback condition. Okay, it is in negative feedback condition. See, negative feedback condition, it doesn't only mean that you are connecting the the negative terminal of the op amp, or else the inverting terminal of the op amp with the V out. Okay, through the resistor only. It can be through any component, or else it can be even without a component. If you directly short the this particular terminal with the V out, so automatically it is considered as a negative feedback condition. Okay, but here in see in case of earlier examples that we have seen, here we are having one resistor, right? Here we had some resistor, okay, which we call it as the RF, okay, feedback resistor. But here we are using CF, which means feedback capacitance, feedback capacitor, or else it is having feedback capacitance. So let's assume that the voltage across this particular capacitor, okay, feedback capacitor, is VC, subset C. Okay, so VC, let's assume VC be the voltage across the capacitor in the negative feedback path. Okay, so now here we are supplying IN as the input current, right? So now IN is become equal to IC. Okay, IN becomes equal to IN is equal to IC. So how to calculate IN? Because see, how many of you know about ideal characteristics of an op amp? Ideal characteristics of an op amp. Actually, this is a huge session. So discussing about the ideal characteristics of op amp itself will take one complete session. Okay, op amps is having an idea. See, actually, the ideal op amp is different from the practical op amp. Okay, ideally we assume something, but practically when we are doing, it is different. So ideally an op amp cannot draw current from the terminals, from the input terminals. Okay, let's assume that you are supplying input voltage IN, right? So actually op amp cannot consume any current from the IN. Okay, it cannot consume any current. Whatever the current which is passing through this terminal, it will directly go from IC, directly it will go through like this. So however, this op amp is not consuming any current. It should not draw any current. Okay, so which we call it as high impedance. Okay, high impedance. So input pins of op amp will have high impedance. So what does high impedance mean? So ideally it draws no current, but in case of practical condition it will draw little current. Okay, that is again different concept where you will be learning about biasing current and compensation resistors. So all these things is a different concept. Okay, so as of now what you need to understand is, like, we are assuming that the op amp that we are using is an ideal op amp. Okay, so if you assume that the op amp that we are using is an ideal op amp, whatever the current which is supplied over here, IN, which becomes equal to IC, because there is no other path for the current to flow. So IN must be equal to IC. So to calculate IN, Vin minus 0 by R. See, already I told you the concept of virtual ground. So here the input voltage is Vin. So Vin minus 0. This is the potential difference across the resistor. Okay, actually from Ohm's law, I is equal to V by R, or V equal to IR. From that we obtain I is equal to V by R, where V is the potential difference across the component. Okay, so potential difference across the resistor R is Vin minus 0. So Vin minus 0 by R equal to IC. So now again here we need to again calculate IC. So basically what we are doing, first we are calculating the value of IN, and then we are calculating the value of IC, and then we are equating IN with IC, and then we are deriving the further expression. So already you know, you might have studied capacitors and its related equations in your lower standard. In capacitors, Q is equal to CV. This is the very basic formula. Q is equal to CV, or else C is equal to Q by V. So capacitance is the ratio of charge, stored charge by voltage, potential across the capacitor. Charge stored by potential across the capacitor. That is the formula for capacitance. So now Q is equal to CV, right? We are differentiating this equation for one time. So what you will be getting on LHS, dQ by dt is equal to C into C is the constant. Every capacitor will have a constant capacitance. So C into D into V by dV by dt. So already here I assumed that the potential across the capacitor is Vc. So that's why I am replacing, instead of V, I am putting Vc. So from Q is equal to CV, we obtained dQ by dt is equal to C into dVc by dt. So substitute this equation. Okay, substitute this equation. See, already you know dQ by dt is equal to IC. Okay, current means rate of flow of charge, right? Rate of flow of charge is nothing but current. So if some electrons or some charge is flowing with respect to time, the rate of flow of charge is nothing but current. So that's why dq by dt can be replaced with IC. IC means current across the current flowing through the capacitor. So IC is equal to C into dVc by dt. So which is nothing but the current flowing through the capacitor. So we know that the current flowing through the resistor is equal to the current flowing through the capacitor in this scenario, because op amp cannot draw any current. Op amp cannot draw any current. Okay. So actually this resistor, what it actually do is like it you know limits the flow of current. Okay, it limits the flow of current, but here current but the current is same. Okay, ideally the same current should flow through it. Yeah, so equating these both equations from 1 and 2, so V in by R is equal to CF into dVc by dt, where CF is the forward capacitance, sorry, feedback capacitance. So V in by R is equal to CF into dVc by dt. Okay, now again what I'm doing, I'm calculating Vc, okay, which is the potential across the capacitor. I'm calculating the potential across the capacitor. So what is the potential across the capacitor from the circuit diagram? Can anyone tell me what is the potential across the capacitor? See, here we are having 0 volt, okay, because this terminal of the capacitor is connected at this node. Okay, so this node is acting as at this node, by applying the concept of virtual ground, the voltage at this node is 0. Okay, and this another terminal, so if this is a parallel plated capacitor, so the another plate is connected to the V out, it tied with the V out, so that's why the voltage at this terminal is V out. So what is the potential across the capacitor? So it is 0 minus V out. Okay, 0 minus V out. So I'm replacing Vc with 0 minus V out. So let's see what's the equation we obtained. So finally we obtained V in by R is equal to minus of CF into dV out by dt, where V out is the output voltage. Okay, so now what I am doing right now is I am just rearranging the equation. On the LHS I am having V in by R, and on the RHS I am having minus CF into dV out by dt. So I am just rearranging the equation. I am moving all other terms other than dV out by dt. I am moving all other terms to the another side. So finally by rearranging I will get dV out by dt is equal to minus 1 by R into CF, feedback capacitance, into V in. Okay, here I represented it as V in of t. See, here t means it's not another variable, it's not V in into another variable t. So here I'm just trying to indicate that input voltage is a function of time. Okay, if you provide some sinusoidal wave, so that sinusoidal wave, it is a signal, it's a voltage signal with respect to time, right? So just to indicate that it is a function of time, I have give me a second. Yeah, so I have written it as a function V in of t, or else you can simply write it as minus 1 by R into CF into V in. Okay, it is also fine. So here what is dV out by dt? It is the rate of change of output with respect to time. What dV out by dt indicates that it is the rate of change of output voltage with respect to the time. Now what I am doing is like I am integrating this equation on both sides. So apply integration on both sides, what you will get? So integration of differentiation, both will cancel out, finally you will get V out of t, where output voltage is also with respect to the time. So output voltage is equal to, see, R is constant, CF is also constant. So since it's a constant, I am writing integration symbol. So minus 1 by RCF into integration of V in of t into dt. Okay. So this is the final equation. V out of t is equal to minus 1 by R into CF into integration of V in of t into dt. Okay, again I am explaining the terms in this equation, where V out of t is the output voltage, okay, output waveform that we obtain, and R is the resistance, okay, and CF is the feedback capacitance, and V in of t is the input signal. Okay, and we are integrating with respect to t. So this is the final equation we obtained. So yeah, I will explain why we have written plus V out of 0 plus, okay, later. But as of now, you can skip this particular thing. I will explain about this thing later. So as of now, you just focus on the equation V out of t is equal to minus 1 by R into CF into integration of V in of t into dt. So from this equation we can observe one thing, that the output voltage, you know, the output voltage which itself is a function of t, okay, it is varying with respect to the integration of the input voltage. So in simple words, output voltage depends upon the integration of the input voltage, isn't it? Because see, from this mathematical equation it already clearly establishes a relationship between the output voltage and the integration of the input voltage, isn't it? So output voltage is the integration of the input voltage. This is the important conclusion that we need to obtain from the this particular equation. Okay, output voltage is a function of the integration of input voltage. This is very important point. I repeat, the output voltage is the function of the integration of input voltage. So up to here everything is clear. Everything clear? See, we derived an expression which states that the output voltage is a function of integration of the input voltage. Okay. See, all we did is like we have replaced the resistor with a capacitor. That's it. All we did is like just replaced the resistor from the earlier scenarios we discussed related to the summation, averaging, all these operations. So in the negative feedback path we are having a resistor, right? We replaced that RF feedback resistor with the CF, okay, feedback capacitor. That's it. See, already I told you this happens only if we use reactive elements. Okay, if you put a resistor is a linear element. It cannot perform integration. If you put capacitor, then it can perform integration. Okay, because capacitor and inductor both are reactive elements. I already told you that an op amp can act as an integrator only if you use a reactive element, not a linear element. So both capacitor and inductor are reactive elements, but capacitor is used, not the inductor. Capacitor is used. Okay. See, actually in case of summation operation, what actually happened is like in place of CF we had a RF, okay, one resistor is there, and here for we have applied some input volt, V1. Earlier we assumed that we have provided three signals, right? I think so, three signals. One is with V1, V2, V3, I1, I2, I3 are their respective currents. R1, R2, R3 are there resistors across the individual signal pathways, and all these resistors are connected in parallel with each other. Okay, I mean they are actually connected at virtual node. Okay, we should not directly say that they are in parallel. So actually they are connected at the at the node where actually the voltage becomes zero. Okay, virtual ground. Yeah. So that's the thing we discussed yesterday. We replaced that resistor with the capacitor and we derived the mathematical expression, and finally we ended up with the equation which is having V in. Okay, from this equation we can understand that output voltage is the function of the integration of the input voltage. Yeah. See, you have provided a sine wave. For example, if the input voltage is sine omega t. Okay, I hope that you know the equation for sinusoidal wave, right? So y is equal to a sine omega t plus or minus phi. Okay, where phi is the phase angle. Okay, y is equal to a sine omega t plus or minus phi. Okay, a is the amplitude. So here let's assume for simplicity it's a sine omega t, or else sine theta. Theta is equal to omega t. Okay, I have written in place of theta I have written omega t. So this is the input signal and this is the output signal. I have got cos omega t. Okay, see, I have not got an inverted output of cos wave. Okay, I have not got inverted wave of cosine function. So why? Because already we are operating it under inverted integrator. Okay, it is an inverted integrator. So if you do the integration with the help of non-inverted integrator, then you will get this output would become 180 degrees. It will 180 degrees phase shift will be there, upside down. Okay, so but here I'm getting directly, if you pass sine wave as an input input signal, you will get cosine wave as the output. So for example, I have provided a square wave. Okay, if I provide a square wave, you will get triangular wave. Okay, so is this clear? So uh, how we can generate a triangular wave with the help of op amp, with the help of integrator. If you run any kind of op amp as an integrator by taking help of reactive elements like capacitor, and you are having one capacitor which is called as feedback capacitor in the negative feedback uh, uh, in the negative feedback condition, and if you pass if you pass a square wave or a square pulse as an input signal, you will end up with getting output as a triangular wave. So by this mechanism you can produce triangular wave also. So isn't it amazing that for an op amp you are giving a square wave, square pulse, and at the output section if you check the output, the waveform you are getting a triangular wave. Okay, now the question is, one more point is like, based on what parameter these the amplitude of the waveforms depend upon. So amplitude depends on the resistor that you have chosen and the value of capacitance for the capacitor that you have chosen. Okay, depending upon the values of R and CF, the amplitude varies. Okay, this is one important point. Based on the values that you choose for resistor and capacitor, I mean the resistance and the feedback capacitance. So based on those two parameters, amplitude varies. So amplitude is dependent on the values that you choose for the components. It could be reactive component or it could be linear component like resistor, or it could be a capacitor. Okay. Yeah. So this is how an op amp can be used for as an integrator, used as an integrator. So I hope it is clear, right, everyone? Everyone, is it clear? So now I'll ask you one question. So we already know that V out of T, okay, V out of T, that means the output voltage is equal to minus 1 by R into CF into integration of V in of T into dt. So now what value, how you need to choose values for R and CF in such a way that the function is completely entirely dependent upon the integration. Okay, the function entirely depends upon the integration, no other scaling factor. Okay,
Both must be unity.
so actually it should be 1 by R into CF should be equal to 1. Okay, so if that means CF is equal to 1 by R, or else R equal to 1 by CF. So this is the condition. So if R is equal to 1 by CF, or else if CF is equal to 1 by R, okay, or else R into CF is equal to 1. This is the condition. R into CF is equal to 1. So then the entire function is purely dependent upon the integration of the input signal. The output wave is completely entirely dependent upon the integration of the input signal, but the final value is the inverted value because you are having a minus sign before it, right? So that means here minus 1 as the scaling factor actually. So we should not blindly say that there is no scaling factor. The scaling factor become equal to unity. Okay, becomes equal to unity. So this scaling factor can be represented with the letter A, right? A or AV. So A is equal to 1. Okay. So here it's a minus 1 because minus indicates that the signal is inverted. Okay, I hope it's clear, right? Now how an op amp can be used for the integration purpose. Now we'll discuss one more concept and we will jump into simulations. Okay. First we'll generate some graphs in MATLAB. So after generating the graphs in MATLAB, MATLAB Simulink, then you can, then in the next session, we'll be doing the schematics of op amps for different cases by taking different values of R, C, all these things. We will perform all the operations like summation, averaging. So, and then we will produce some graphs, and from graphs we will recheck whether our, our theory and our theoretical calculations, how it is deviating from the practical values. Okay, in KiCAD with the help of a spice simulation we will do that. Okay, so now we will go with the graphical analysis of slew rate, how slew rate affects on pulse signal. So here we are primarily discussing two things. The first thing is how this slew rate affects on pulse signal, and the second thing is how this slew rate affects on a sinusoidal wave, sinusoidal signal. So there are so many signals, but we are not discussing about all the signals. We are discussing only about two signals. So one is a pulse signal, square pulse, and the second one is effect of slew rate on sinusoidal wave. Okay, so let's assume that, so you have given this yeah, before this I want to ask you one question. So I'm just going back to the earlier schematic. So what is the voltage at this node? What is the voltage at this node?
0.
Yeah, because of a virtual ground, right? So now I will do one thing. Instead of connecting the non-inverting terminal to the ground, see this triangle I have written over here, it actually indicates the it's another way to represent ground. Okay, ground symbol. So I have tied the non-inverting terminal to the ground. But if in case, if I do not tie this non-inverting terminal to the ground, and rather I'm also providing some input voltage to this non-inverting terminal also. Let's assume that I'm supplying 3 volt to the non-inverting terminal. Then what do you think would be the voltage at this particular node? The junction which is formed between the negative feedback loop and the inverting terminal. What do you think the voltage at that junction?
Can you repeat again?
So here what actually happening is, in this particular circuit diagram, I have connected the non-inverting terminal to the ground. Okay, is this clear? I have connected the
low load
non-inverting terminal to the ground.
ground.
Do you agree?
Yes.
Yeah, this is the another way to represent the ground. Just a triangle, right? This is another way to show the ground. So now what I am saying is, like, at this specific scenario, when I tie this non-inverting terminal to the ground, the voltage at the junction which is formed between the negative feedback loop and the inverting terminal is 0, because we discussed about the virtual ground, because of the virtual ground concept. Okay, this particular node acts like a virtual ground. Now my question is, instead of tying this non-inverting terminal to the ground, if I connect this terminal to some, if I also provide some voltage to the non-inverting terminal, that which is the positive one, the positive terminal, let's say for example I have supplied something like a 3 volt to the non-inverting terminal, then what do you think the voltage at this node? Do you think it still remains 0, or what changes, what will happen to that node?
I think it remains the same.
Actually it will become 3 volt. Okay, it will become 3 volt. So whatever the voltage that you apply to the another terminal, so this node takes the same voltage. Okay, so whatever the voltage that you apply to the another terminal, let's say you are operating it under negative feedback condition, and negative feedback means you are using the
Stable.
inverted terminal. Okay, see, since in this specific scenario the non-inverting terminal is connected to the ground, where for the ground it is 0 volt, right? So that's why this particular node is acting as a virtual ground. So what virtual ground means, it is nothing but it will take the same voltage of the other terminal. Okay, it will take the same voltage. If instead of ground here, if you supply 3 volt, the voltage at the virtual ground becomes 3 volt. It becomes 3 volt. It will take the same voltage. If you provide 5 volt over here, it will take 5 volt. If you tie the another terminal to the ground, then only this particular node is called as the or else then only it is called as the virtual ground, because it is taking 0 volt. Is that clear?
Understood.
Is it clear, or shall I need to repeat again?
Understood.
Yeah. See, actually, all these are special properties of op amps. Okay. Yeah. Now we are discussing effect of slew rate on pulse signal. Okay. So now you are not operating the op amp. Okay, you are not operating op amp in neither the positive feedback condition nor the negative feedback condition. That means you are not tying the output voltage to any of the terminals, okay, between inverting and non-inverting terminals. So basically you are having an inverting terminal and a non-inverting terminal, and you are having an output. Okay, so yeah, see, in that condition, okay, so what happens is, if you provide some input to for example, you are providing something like a 5 volt, okay, 5 volt to the see, here it's a square, it's a pulse signal, okay, it's a pulse signal over here. But assume that if it's a something like a straight line, okay, that means no frequency. If you take a DC voltage, so for DC there will be no frequency, isn't it? Frequency of a DC signal is 0. For AC waves, for AC signal only there would be frequency, okay. In case of DC signal, there is no frequency. That means straight line will come, right? So you are producing, let's assume that you are giving 5 volt input to the non-inverting terminal of an op amp, and if you check the output, so what do you think the output could be? Any idea? You understood the question first? You are giving some 5 volt input to the non-inverting terminal, let's assume, and you are checking the output. Okay, you are not operating it under any kind of negative feedback condition nor the positive feedback condition. Just you are giving some 5 volt input and you are checking the output. So what do you think the output could be?
Same 5 volt.
Yeah,
5
you will
volt.
get. Sorry, Nihal is saying some other thing. Yeah, what's your answer, Nihal? Oh, I think it's Prakash Sharma. Yeah, you are saying something, Prakash. Yeah,
Sir, 5 volt.
5 volt. Yes, so we expect that the output will be same. Okay, so output we assume that it will be same. So now similarly here, let's see, this is the whatever the graphs that I'm presenting you right now, all these graphs are actually experimented in the same situation, okay, where you are not operating it under negative feedback or nor positive feedback condition. Just you are giving an input and you are checking the output, okay, nor even this is operated in the inverted amplifier, nor even the op amp is acting as an inverted amplifier, okay. So it is non-inverted amplifier only, because you are giving the signal to the non-inverted terminal, which is represented with the positive sign. So let's assume that here I am passing some square pulse, okay, square wave pulse. So in this particular first example that I'm showing you, the time period is 40 microseconds. Okay, time period is 40 microseconds, because time period means you need to check the portion of the graph which is repeated, which is being repeated every time. So it is the graph started at here, and this particular first it is increasing and then again decreasing, and it is remaining in the low state for some time. So from here to here it is one cycle, okay. So that's why the time period is calculated for one complete cycle, so which is 40 microseconds, okay. Among these 40 microseconds, for 20 microseconds, that means for the first half of the time period, it is remaining in the high state, okay. That means you are supplying 5 volt, and this pattern continues. Now we will check the output. For simplicity, we are taking only the first thing, okay. We are taking only the first thing, not we are keeping this other pulses aside, okay, other square pulses aside. We are taking the first one for simplicity, and we will be checking the output. So what we expect is, like, we will again get the same thing, okay, like the 5 volt, the same square will be coming in the output. But actually what happens is, like, you will be getting something like this, which is having some slope, some inclination. See, it is this particular line is inclined with the horizontal x-axis, okay, and it came like this. So this is the output characteristic. For input you have given a square pulse, but ideally you expect that it will give the same thing, but practically it is something like, like this, okay. So now how to understand, like, let's assume that you are given the square pulse, then how can you determine the output waveform? So to determine the output waveform, the important parameter that you need to know is like what is the slew rate of the diode. Okay, and again I repeat, if slew rate, if let's assume that you have taken two different diodes. Okay, I'll just come back to one more previous slide where we discussed about slew rates for different kinds of op amps. For LM741 it is 0.5 volt per microsecond. For LF411 it is 15 volt per microsecond. For LM318 70 volt per microsecond. LM6364 it's a 300 volt per microsecond. And similarly for LT1363, which belongs to linear technology, it is 1000 volt per microsecond. Okay, so let's assume that you have taken two different op amps. One is LM741 and another is something like LT1363 or LM318. So for both these two different op amps, slew rates are different. So if slew rates are different, again the output waveform that you are obtaining is also a little bit different, because the output is affected by the slew rate. Okay, output is affected by the slew rate. So what does this slew rate indicate? What does this slew rate indicate? So this slew rate indicates that for 1 microsecond, the output voltage can vary, up to 0.5 volt. Okay, in 1 microsecond, the output voltage can vary up to 0.5 volt. So this is what actually a slew rate indicates. So here in this particular scenario, see, actually it is little bit difficult to understand, but try to focus on the concept. So if you understand only one graph, rest all other graphs you can predict yourself. Okay, I already told.
Triangular.
Sorry. So coming back to this concept. So just try to understand this graph. I will explain you. So other graphs you can try predict on yourself. So here the time period is 20 seconds. So time period is 40 microseconds, right? So now what you need to do is, first, the first half of the cycle is called as T1 by 2. Okay, half cycle, first half cycle, and this is the second half cycle. So first we will check for the first half cycle. This is 20 microseconds. So I'm multiplying this 20 microseconds with the slew rate. So 20 into 0.5. 0.5 means 1 by 2, right? So half of the 20 microseconds is nothing but 10 microseconds. Okay. So to reach 5 volt, the particular op amp requires 10 microseconds. Okay. It requires 10 microseconds to reach 5 volt. So from this you can understand that if you provide some input signal, okay, of some voltage, at the output to reach that voltage it will take some time. To reach that voltage it will not directly immediately, as soon as you supplied the 5 volt input, it will not immediately, the output waveform immediately may not able to take up the applied voltage. It will take some time. Okay, there will be little bit delay, it will take some time, gradually it will reach the supplied voltage. So this time taken is directly dependent upon the slew rate. So slew rate is affecting a lot, isn't it? So now now we will check how this graph came. So I'm multiplying this 20 microseconds with the 0.5 volt. You got 10 microseconds. So for it takes 10 microseconds to reach 5 volt. See, I told you that this is 20 microsecond, right? So again if you just draw a line, okay, if you divide this symmetric wave into two halves, in the first positive half cycle, I mean in the first half of the time period, if you draw a line over here symmetrically, so you can divide this particular square pulse, okay, the first portion into two different fragments, where the first fragment is 10 microsecond and another one is 10 microsecond, right? So that's why I already told you that since the slew rate is 5 volt per microsecond, so it will take 10 microseconds to reach 5 volt. So 10 microseconds means that 10 microsecond will, see in this graph on the x-axis we are taking time, on the y-axis we are taking the voltage. So here it is 0 volt comma 0 seconds. So here it is 0 volt comma, I'm talking on the x-axis, because on x-axis y values are always 0. So at this particular point, the coordinates would be 10 comma 0. Okay, that means 10 microseconds is the time, and the y value voltage would be 0. So now here if you take at this particular position, what would be the coordinates? It would be 10 microseconds comma 5 volt. Okay, 10 microseconds comma 5 volt. That's what I told you. So it will if the slew rate is 0.5 volt per microsecond, so it will take 10 microseconds to reach 5 volt. Okay, so that means the graph starts from this particular position and it will reach over here. Okay, and as long as this 5 volt stays in high position, so till that it will stay in high position, and again it will take 10 microseconds to reach 0 volt. Again it will take 10 microseconds to 0 volt. So is this clear? That's how this waveform is obtained. Is it clear, everyone?
Yes.
Okay. So now here important thing is like output signal is now getting distorted. Do you agree with this statement or not? Output signal is getting distorted. Everyone agrees with the statement output signal is getting distorted. Hello.
Distorted.
Yeah, guys, I request kindly please try to respond, or else I will end the session, because if you do not respond, I cannot explain. Okay. So output signal is now getting distorted. Now we are taking another example, okay, of the same square pulse. Okay, of the same square pulse, here different conditions have been provided. The first one is time period is 20 microsecond. So this is question, okay. One question is this is one of the illustration. So the here it is said that in the question it is said that the time period is 20 microsecond and the on time, okay, on time is 10 microsecond, and slew rate is 0.5 volt per microsecond. So then see, actually we are see in this condition we have provided a square wave and we got something like a distorted wave. So it was like this, right? But here in this scenario what actually happening is you are applying the square wave, but at the output you are getting a triangular wave. So we have seen this triangular wave twice, where when you integrate a square wave, okay, when you integrate a square wave, ideally if you assume that there is no distortions, and then you will get a triangular wave if you do the integration. So again if you take an ideal op amp, if you supply a square wave, at the output section also will get a square wave. But practically what's happening here, if you provide the square wave, directly you are getting a triangular wave, isn't it? But depends upon the condition. So let's see these conditions. In this particular scenario you have given a square wave, but in the output you got a triangular wave. Okay, let's see the condition and we will check how we got a triangular wave when we have given a square wave. So it is given that the time period of the input signal is 20 microsecond. Okay, so that means actually from 0 to 10 it stayed high, and from 10 to 20 it stayed low. So this is the actual input signal is like, so this particular thing, okay, up to here 20. So this is also part of the input signal. This is also part of the input signal. Okay. Yeah. So now it is said that the on time is 10 microsecond. Yeah, it is said that the on time is 10 microsecond. That means the op amp, despite the time period is 20 microseconds, the op amp remained in the on state. That means you are the op amp is working functional for only 10 microseconds. Okay. So first what we need to do is like, so let's assume this is the maximum voltage, right? This is the maximum voltage, input supplied voltage. To reach this maximum voltage, first let's check how much time it requires, the op amp requires to produce the output. So for that what we need to do, we need to simply multiply the time period with the slew rate. 20 into 0.5, which is nothing but 10 microseconds. So you started from 0, okay, it requires 10 microseconds, right? So yeah, at this particular position the coordinates are 10 microseconds Vmax. Okay, here Vmax means whatever the maximum voltage that you applied. So again it is taking 10 microseconds to reach the 0 volt. So by this way you got a triangular wave. Okay. See, this is another condition. This is one more scenario where you are getting a triangular wave, but the maximum amplitude of this triangular wave, it is not as same as the input. Here the amplitude of the maximum amplitude of the triangular wave become equal to the maximum amplitude of the square pulse. But here in this condition both amplitudes are different. This amplitude of the triangular wave is exactly half of the maximum amplitude of the square pulse, okay, or else a rectangular wave provided. Okay, so these are different conditions. This is the effect of slew rate on what? It is the effect of slew rate on pulse signal, pulse wave. Now we need to see the effect of slew rate on sinusoidal wave. So you know that for sinusoidal wave, v of t, the equation is v of t is equal to vm sin omega t. Okay, sometimes people usually write it as a sin omega t. Here A is the maximum amplitude. So maximum amplitude in the sense maximum voltage. That means Vm. Vm means maximum voltage or Vmax. V of t is equal to Vmax sin omega t. So I'm differentiating on both sides. So dV by dt is equal to Vm omega into cos omega t. This is this can be obtained by differentiation. So now what I'm doing is I'm just replay, for cos omega t, what is the maximum value of cos? The maximum value of cos is 1, right? For sin it is -1 to 1. For cos the maximum value is 1. So I'm taking the maximum condition. So I replace it the omega with 2 pi into f, where f is the frequency. Okay, and cos omega t I replaced it with 1. And dv by dt max is equal to Vm into 2 pi f. So actually in case of sinusoidal wave, so already we discussed that what is the slew rate. Slew rate means the rate of change of output. Okay, the rate of change of output is nothing but slew rate. Okay, how fast the output voltage is varying. See, all the time we discussed about the slew rate, the units are in volt per microsecond. Okay, in 1 microsecond how much voltage can it change? That is nothing but slew rate. So this dv by dt I can replace it with SR. SR is nothing but slew rate. So we must take the slew rate which is greater than or equal to Vm into 2 pi f. Okay, we are not going into detail, just as of now you need to understand that dv by dt max, it is nothing but the slew rate. Okay, so up to here we are not going in detail about graphical analysis of sinusoidal signal. Just try to understand only the graphical analysis effect of slew rate on square pulse. So up to here I hope everything is clear, right?
Yes.
Everything clear? Yeah. So basically what we discussed today, we discussed how an op-amp can be used as an integrator, where in place of RF we replaced it with CF, and for CF we have taken the equation from Q is equal to CV, we differentiated on both sides. dQ by dt is equal to CF into dVc by dt, and dQ by dt is nothing but IC, current through the capacitor. So IC is equal to CF into dVc by dt, where Vc is the voltage across the feedback capacitor, so which is nothing but 0 minus V out. Okay, Vc is equal to 0 minus V out. So from the schematic circuit diagram we obtained it. Vc is equal to 0 minus V out, so which is nothing but minus V out. Okay, so finally we obtained the equation IC is equal to, I will show you that slide. Yeah, so finally we obtained the equation IC is equal to, where is it? Yeah, C into dVc by dt, where this Vc can be replaced with minus V out. So IC is equal to minus C into dV out by dt. Okay, we obtained this equation, minus CF into dV out by dt. And on the right side we are having I in. Okay, I in, input voltage. Okay, input current. So I in, we also derived for I in. I in is V in by R. Okay, so finally we equated both the equation. V in by R is equal to minus CF into dV out by dt. See, here also dV out by dt is nothing but the slew rate only. Okay, yeah. So now we have kept dV out by dt on one side, and then we have by rearranging the equation by transferring the other terms on the all the other terms to the another side. So finally we got the equation dv out by dt. See, actually dv out by dt max is the slew rate, not just directly the dv out by dt. Okay, so dv out by dt is equal to minus 1 by r into cf into v in of t. So by integrating on both sides, integration and differentiation, integration of dv out by dt into dt. So dt get cancelled, integration of dv out becomes v out. Okay, so integration and differentiation basically get cancelled. You will get v out of t is equal to, where v out output voltage is the function of time. So v out of t is equal to minus 1 by rcf into integration of v in of t into dt. So from this equation, it is very clear that output voltage is a function of the integration of the input voltage. And if you take, if R into CF is equal to 1, then V out becomes V out of t is equal to minus integration of V in of t into dt. Okay. And we discussed about two examples. If you provide a sine wave, you are getting a cosine function. And then if you are giving some square pulse, you are getting a triangular wave. And we discussed about the effect of slew rate on square pulse and the sinusoidal wave. And so actually this op-amp can also be used as an integrate for logarithmic operations. Okay, op-amp can also perform logarithmic operations. So this is basically, yeah. So the first operational, here is one theoretical point. The first op-amp was produced in United States. Okay, the first op-amp is produced in United States. So this is the block diagram for logarithmic function, how to do logarithmic operations with the help of op-amp. So we are not going in detail about, because the derivation is complicated, we are not going in detail about logarithmic, but still I will try to explain. I will try to give you a basic overview. Okay, yeah. So now we are discussing about yeah, someone raised your hand. Yes, Prakash, you have any questions?
No, sir.
Okay, okay. And Nihal Reddy is asking the question, is recording available for today's session? No, recording is not. Current session is being recorded and streamed in the YouTube. However, maybe the recording may not be provided by the admin team. Okay, because this is also part of the lab session. Already it is informed yesterday that this is the lab session. Okay, op-amps is part of the lab session. Due to, since it's a huge session, we, fragmented into multiple parts. However, I will request the admin team to send the recording, but ultimately it is in the discretionary power of the administration team. Okay, I will send a message. I will send a message to the admin team to provide the recording. They will update you in the group. Okay. Yeah. So now we are in the next concept. From here, I request everyone to focus from here, because it is very complex and to understand as well. So in this particular thing, if you want to make an op-amp to do logarithmic operations, here we are replacing the capacitor with the diode. Okay, we are replacing the capacitor with the diode. See, in case of integration, we have used the reactive element, which is nothing but capacitor. In case of other operations like the scaling operation, averaging operation, and inversion operation, scaling, inversion, and summation. So for all these three operations, we have used the resistor. And in case of integration, we have used the capacitor. It is a reactive element. Here we are using an active device. Okay, we are using an active device, diode. Okay, we are using diode. Okay, so again the same thing, just we have replaced the capacitor with diode. See, this is the beauty of electronics, the art of electronics. Just by replacing the resistor, it became an integrator. Just by replacing the resistor with capacitor, it became integrator. Just by replacing the capacitor again with the diode, it became an op-amp which can perform logarithmic operations. So electronics is always a huge interesting subject. So just by, it's a really very amazing thing, isn't it? Just by replacing the capacitor, the reactive element capacitor with a diode, now it is having the capabilities to do the logarithmic operations. Okay, yeah. So for diode there is one equation. Okay, see, if you are placing a capacitor in the negative feedback path, then what is the equation that you need to know about it? You need to know the basic fundamental equation of the capacitor, fundamental equation of the capacitance. Am I correct or not? Because from Q is equal to CV only we derived the everything. Just by differentiating the equation Q is equal to CV, finally we ended up with getting an equation which establishes a relation between the output voltage. Which states that the output voltage is a function of the integration of the input voltage. Maybe there is some scaling factor. If you choose R and CF, if you R into CF, if you take it as 1, then it becomes exactly equal to integration. Okay, so again similarly here, if you are placing a diode in the negative feedback pathway, so first you need to know the equation for the diode. So there is one famous equation in diode. ID is, see, don't ask me for the derivation for ID is equal to this particular diode equation. Okay, because the derivation for this equation is not part of our session, so it is beyond our scope. So but as of now I'm just quoting that equation over here, because this equation we are using to further derive the an expression which states that, from which we can understand that the op-amp can able to perform the logarithmic operations. Okay, so this is the diode equation. ID is equal to Is into e to the power of Vd by neta Vt minus 1. Okay, neta into Vt minus 1. So where Is is the reverse saturation current and Vd is the forward voltage of the diode, and neta is the ideality factor, and Vt is the thermal voltage. Okay, and ID is the current across the diode. Okay, see, in the previous case what we did, IR is IR or else IN. Okay, you can take as IN. So IN is equal to IC, isn't it? In the previous condition, in case of integrator, so what we did, IN is equal to IC. That is the condition, first condition we have written. Because ideally a diode draws zero current because of the high impedance to the inverting and non-inverting terminals. So similarly here also ID is equal to current flowing through the diode is equal to current flowing through the resistor. IR is equal to ID. Okay. So for calculating IC, we have derived an expression from Q is equal to CV by differentiating Q dQ by dt, which is nothing but IC. So similarly here also, first we need, unless we know the current flow, what is the formula for current flowing through the diode, you cannot derive the expression. Okay, so this particular expression gives the current flowing through the diode. Okay, so coming to this neta, so this neta is the ideality factor. Okay, this ideality factor can vary from 1 to 2. So neta can take value from 1 to 2. So here there is one important point, very very important point. So actually making op-amp to perform the logarithmic functions is not that much easy as we did for integrator or the other stuff. Okay, it is a little bit complicated. Here temperature also plays an important role. Okay, so actually there are two different things. One is temperature compensated logarithmic amplifier, logarithmic op-amp, and another one is temperature non-compensated logarithmic operational amplifier. Okay, even in logarithmic operational amplifiers, so again two categories. One is temperature compensated logarithmic operational amplifier, and another one is temperature non-compensated logarithmic operational amplifier. One is temperature compensated and another one is temperature non-compensated. So what does it mean we are using the term temperature? So temperature means even the external temperature can affect the operations of a diode. Okay, so that means temperature plays an important role. So if you place this diode under under the fire, okay, and you give the input, and if you try to get the answer, so answer there would be little bit error in the answer. So it may give a nearest answer, but the actual value it differs slightly. There would be small deviation, okay, from the actual result. So it is not 100% accurate. Okay, in case of temperature non-compensated. In case of temperature compensated, accuracy and precision of the output is higher than the temperature non-compensated. So we cannot directly rely on the temperature non-compensated. We must use temperature compensated logarithmic amplifier. Okay. So actually current across the diode is highly affected by the temperature. Okay. Temperature of the diode. It is highly affected by the temperature of the diode. So now there are, see, if you check this particular equation, ID is equal to IS into, IS is the reverse saturation current. ID is equal to IS into e to the power of VD by neta into VT. Here there are two terms which depends on the current. Okay, there are two parameters which depend, sorry, not current, temperature. There are two parameters which depends on the temperature. What are those two parameters? The first parameter is the IS. IS means reverse saturation current. And the second parameter, as the name suggests, thermal voltage. Okay, it is due to thermal agitation. Okay, thermal excitement. So due to the temperature. So this VT and the and IS, these two terms depend on the temperature. Okay, they highly depend on temperature. So IS and VT are temperature dependent parameters. Okay, so all these questions may be asked in the quiz session. So among neta, ideality factor, forward voltage of the diode, and reverse saturation current, thermal voltage, which parameters are dependent upon the temperature. So reverse saturation current and the thermal voltage, these two parameters are dependent upon the temperature. Okay, and neta is called as the ideality factor. And neta can take values from 1 to 0. It can be 1, it can be 2. So if it is 1, then it is called as ideal diode. Okay, practically the value can be anything in between 1 to 2. It can be 1.5 or depending upon the manufacturer. Okay, see, all these parameters are there. Electronics is not that much of easy. Just if you make some kind of schematic and if you run it, that's not, see, actually most of the people usually ask me a question that I made a PCB and I get it fabricated, but after fabrication I have given the input, but I am getting a weird output, not the expected output, or else it is malfunctioning, or else some dysfunction. Okay, I'm not getting the expected output, I'm getting some other waveform or some other unexpected thing is happening, it is not working. Because all you guys are doing is like you are just only focusing on the schematics, but you are neglecting the what happening. You don't know the mathematical analysis, you know nothing. So if you just simply think, like if you just blindly believe in that, see, if we have already taken the case study of the operational amplifiers, we discussed about the slew rate. So for those people who don't know about slew rate, for example, they have chosen some other, I have chosen one kind of one kind of op-amp which is having some slew rate, and you have made a PCB with the help of a diode having some other slew rate. So you should not expect that our both PCBs should get the same output, because see, in the schematic it is same. Okay, yeah, everything is same other than the op-amp that we have used. Maybe I have used LM741, you have used something from linear technology. Okay, so maybe the op-amp that we have used is different. Apart from this, the entire schematic could be same. Okay, exactly same, and we both fabricated from the same manufacturer. Finally we have given the same input to both the PCBs, and we are checking the outputs. Both outputs are different because the slew rate for both of these op-amps are different, and due to this slew rate, it affects, no matter what, we have already seen the example how the slew rate affects the square pulse and the sinusoidal wave. So it is the output is highly affected by the slew rate. So due to this slew rate, the output is little bit different. So some distortion is there. So without knowing this kind of analysis, so you cannot directly do that. So that's why this is really a ocean of knowledge. The more you explore, the more interesting thing gets, you will start understanding the more interesting stuff. Okay, so you need to dive deeper into the ocean to understand this the knowledge of electronics. So actually electronics, the art of electronics is very beautiful. Okay, the art of electronics is literally beautiful. And also there is one book named Art of Electronics. So I request, so just visit some library and get the book. I don't remember the author name right now. If possible, I will try to send a picture. Just read the book, The Art of Electronics. Okay, I think it is from Cambridge, I think so. Paul Horowitz, Winfield Hill, Paul Horowitz. So just get that book from the nearest library or any kind of from your college, or if it's not available in the college, just visit the central library or any kind of library nearby you and get a book from there and try to go through the art of electronics. Then in that book you can find a lot of useful information. Okay, so here we are discussing about how to use an op-amp for the for performing the logarithmic operations. And here again in logarithmic operational amplifier, two categories: one is temperature dependent and another one is temperature compensated. I don't say the another one is temperature independent, because diode is always dependent upon the temperature of the diode, but the temperature compensated, we are discussing about compensated and non-compensated, not temperature dependent and the temperature independent. No matter you are using temperature compensated or temperature non-compensated, it depends on the temperature. Okay, naturally it is a natural law, it depends on the temperature. But if you do the compensation, the accuracy, the precision of the output value would be high. Okay, so that's why we need to go with the compensated. So as of now in the session we will be discussing only about the non-compensated temperature non-compensated logarithmic operational amplifier. Those who are interested to learn the temperature compensated logarithmic op-amps, and those who are interested more to learn about VLSI, and so for that you can enroll into another course where we'll be teaching the IC design, okay, and PDK, process design kits. In that particular course we will be explaining you. So coming back to this particular session, so first we will see for thermal voltage the formula is Vt is equal to Kt by Q, where K is the Boltzmann constant, T is the diode temperature, okay, and Q is the charge of an electron. So charge of an electron is 1.6 into 10 to the power of minus 19 and coulomb. Coming to the Boltzmann constant, K is equal to 1.38 into 10 to the power of minus 23 joule per Kelvin. Okay, so substitute these values. So K comma Q are constants, right? K comma Q are constants. Only T is the variable here. So what is T? T is the diode temperature. So thermal voltage depends upon the diode temperature. Okay, so nothing but thermal voltage is nothing but the voltage which is produced due to the thermal agitation or excitation in the charges, okay, which is actually equal to the same diode temperature with the scaling factor K by Q, where K is the Boltzmann constant, Q is the charge of an electron. So now see for temperature also we'll take one thing. Let's assume that you are having this op-amp in the room temperature. Okay, we'll take the room temperature into consideration. Okay, so at room temperature it's a 300 Kelvin. So if you substitute 300 Kelvin into this diode temperature, so then the Vt becomes to 25.8 millivolt. Okay, thermal voltage becomes 25.8 millivolt. So even at room temperature 25.8 millivolt is produced, okay, due to thermal excitation. So now what I'm doing is like I'm substituting the value see in place of Vt, okay, in place of Vt I'm substituting 25.8. So 1 by 25.8 it becomes 38.6. So finally we got the equation ID is equal to Is into e to the power of 38.6 into Vd by neta, okay, minus 1. So actually here we need to do some approximation. We can neglect this minus 1 based on some approximations. So finally ID become approximately equal to Is into e to the power of 38.6 into Vd by neta. Okay, this is the equation, main equation. So now what we are doing is like we are bringing this Is from RHS to saturation current from Is to the LHS. So finally we got ID by Is is equal to e to the power of Vd by neta into Vt. Or else see here we substituted the all the values for Vt, Kq by T. K as the Boltzmann constant, Q as the charge of electron, and T we have taken 300 Kelvin for the room temperature. So let's come back to the original equation. We'll keep the same thing, Vt only. So then ID by Is is equal to E into Vd by neta into Vt. This is the universal equation. Okay, this is applicable, this particular equation is applicable only if the op-amp is in room temperature. So this equation you can apply for all the temperatures. Okay. So now what we are doing is like we are applying the natural logarithm on both sides. So apply natural logarithm on both sides. Then natural logarithm of id by is is equal to, see, ln of e to the power of vd by neta into vt. So already you know natural logarithm, for natural logarithm its base is e, right? Okay, for natural logarithm base is e, not 10. So that's why it will become log a to the power of m uh, base a is equal to the m. Okay, this is equation log, you know, it is one of the fundamental equations in logarithmic operations. So from that you will get natural logarithm of id by is is equal to vd by neta into vt. Okay, again I'm transferring this neta into vt from rhs to lhs. Finally we will end up with this particular equation. So vd is equal to natural logarithm neta into vt into natural logarithm of id by is. Okay, so already we discussed in the starting. Okay, here we already discussed that. Yeah, I think I have not explained these three parameters, right? Now I'll explain. So first we need to calculate the I think someone, hello. So v out becomes, v out is equal to minus neta into vt into natural logarithm of id is nothing but v in. V in is equal to id, right? And v in by is into, so actually id is equal to v in by r. Okay, id is equal to uh, ir, current through the diode is equal to current through the resistor. From Ohm's law, ir is equal to v in by r. Okay, by replacing id with v in by r, finally we will end up with getting this equation. V out is equal to minus neta into vt into natural logarithm of v in by is into r. So this is how an op-amp can be used for performing the logarithmic operation. So it is the logarithmic amplifier. Similarly, there is anti-logarithmic amplifier also. So there is anti-log amplifier. So op-amp can be used for anti-log amplifier also. Okay, so in case of anti-log amplifier, we are putting this diode directly, not in the negative feedback path, not in the negative feedback path. We are placing the diode over here, and in the negative feedback path we are putting the resistor only. Okay, feedback resistance. Yeah, so there is derivation for this one also. Finally we will end up with getting the equation v out is equal to minus r into is into e to the power of vd by neta into vt. Okay. So thank you for joining today's session. This is your expert mentor Hemant from Suchana, and this course is presented by Suchana Space India, co-presented by Grow IOTA LLP, and our special partners Ergel Technologies, Anu Electronics Chennai, our all-in-one platform for electronic kits and die kits and components, and also our special partner Luna Energy, our all-in-one solution for EV technology and EV solutions. So thank you for joining today's session of operational amplifier. We discussed about the operational amplifiers, how it acts as with the help of op-amp, how we can do integrations, and how it acts as an integrator. And we discussed about, we did a graphical analysis on slew rate, how this slew rate affects on a square pulse, and how it affects on sinusoidal wave. And we discussed about logarithmic amplifier, inverted logarithmic amplifier. So in tomorrow's session we will discuss about anti-log amplifier. Okay, and then we will do some simulations for these different configurations of op amps, okay, in MATLAB. Yeah.